Okay guys, now that we've talked about position, displacement, average velocity, and instantaneous velocity, we're ready for a new concept, which I sort of hinted at last video, but let's go into that new concept. The new concept is something called, this is, again, hopefully you're familiar with it, but this is something called acceleration. So this is a new concept. Acceleration is a term that's used to describe the way in which the velocity changes. It's the rate at which the velocity changes. And so the way we define this, we say that acceleration is the change in velocity delta v over the change in velocity delta time, delta t. So this is the definition of velocity, right? This is the rate of change of velocity. So that's the definition of acceleration. So that's v minus v naught divided by t minus t naught. And that is another equation that actually is sort of giving you the punchline, but we're going to kind of go into this. We're going to sort of derive this equation in just a minute. So let's think about acceleration. Right here, we left off with this graph. This is a graph of velocity as a function of time. And what's the relationship between the acceleration and this graph? Well, acceleration is defined as delta v over delta t, which would be the slope of this line. In other words, the slope of this line is the acceleration. So without even thinking about calculus, we could go ahead and figure out what the acceleration is. I could say that the acceleration of this line, the acceleration is equal to the slope of this line, which in this case, if we did that, we would take 8 minus negative 4, that's the same thing as 8 plus 4, 12, over 3 seconds, or we could say it is, in this case, 4, positive 4. Now, standard units, if we're in meters and seconds, would be 4 meters per second squared, 4 meters per second, which, what does that mean? That means that every second, the velocity changes by 4 meters per second. So that sort of very non-technical definition of, or explanation of acceleration in this particular case of the car. Let's think about it using a little bit of calculus. Hopefully it's clear to you that when we do this exercise, if we're finding the slope of the line, what we're talking about is the derivative of velocity, and that's true. The acceleration is defined as the derivative of the velocity, dv over dt. And knowing that, we can now kind of work backwards. Let's imagine that we hadn't done all of this work, right? Let's imagine we didn't know anything about the position, that we didn't know anything about the velocities here. Let's imagine we hadn't done any of that work, and all I told you was you have a car, and the car is accelerating at positive 4 meters per second. Let's imagine that that's all we're given. The acceleration is positive 4. Okay? Could you work backwards from that information to figure out something about the velocity or figure out something about the position or the displacement? And the answer, of course, is yes. And let's do that. So here what we're given is that the acceleration is 4. Let's imagine that now as our starting point. And maybe from that starting point you'd like to know something about the velocity of this object. Well, let's start by recognizing that acceleration is just dv over dt. So dv over dt equals 4. And now what we could do is we could integrate this, right? Well, I could take the integral of dv over dt equals the integral of 4 dt. For right now, we're just doing the indefinite integral. And what do we have on the left side? Well, this is just v. So I've got v equals, what is going on the right side here? Well, it's going to be 4t. And then we've got to add this plus c. We've got this constant that comes in. Let's just remember here, this was our starting point. That's our starting point. A equals 4. And now we've got this equation that will allow us to find the velocity at any time t, as long as we know what c is, right? We need to know what c is, otherwise we can't figure out the velocity at time t. So what's c? Well, what would happen if I plugged in 0 for t? In other words, what if I said v naught equals 4 times 0 plus c? Well, we see that, in fact, what is c? C is the initial starting velocity. Okay, so v naught is the same thing as c. And now I can go ahead and say that the velocity at any time t is going to be equal to v naught plus a times t. And that's now going to be a very, very useful equation. Okay? Very, very useful equation. This is true. This is the relationship between acceleration and velocity. If you know the acceleration, the velocity is the initial velocity plus at. This hopefully makes sense, right? The velocity is equal to the initial velocity plus the change in velocity. That's all we're saying. And so going back to the graph here, I could say, well, the initial velocity is -4, the acceleration is 4, and I could derive this equation, right? This is v equals v naught plus a t. Okay, directly from this equation. This is going to be an important one to us. Okay, well, that's all well and good. What if you want to know now an expression that's going to allow us to talk about the position with respect to time? What if I want to know something about the position? Well, we know that the velocity, is the time derivative of the position function. So I could say dx over dt equals v naught plus at. And I could go ahead now and integrate this with respect to time. So I could say dx over dt equals the integral of this whole thing, v naught plus at dt. And what do I get? Well, this is just x equals, what do I have over here? Well, I'm going to get v naught times t plus, what's this going to be? Well, this is going to be a times t squared over 2. And then, of course, I have to add my c in there. And once again, I ask myself, what's c? Well, I can go through this whole exercise again, plugging in 0 for t. If I plug in 0 for t, these two terms vanish, and I see that c is simply the starting position, x naught. And so now I can say x equals x naught, that's my c term, plus v naught times t, plus 1/2 a t squared. Now this is an enormously useful equation. We're going to use this equation a lot. Okay? And I want to point out that this equation is this equation up here, right? This is the same form. What do we have here? This is x equals x naught, starting position, which we knew. We said that the starting position here was 2. Okay? Minus, what is this? What is this thing? This is when we said plus v naught times t. Right? V naught, we know, is -4. We determined that from this graph here. The initial velocity is -4. So this term right here, the -4, is the initial velocity, plus 1/2 a t squared. Okay, so let's maybe, just to make it really clear, the 2 is our starting position. The -4 is our initial velocity. And the 2 is 1/2 of a. Well, if 1/2 of a is 2, and then a is 4. And we know that already. That was our starting point here. Our starting point is this. The acceleration is 4. And so now we've got a couple other equations in our pocket here. We've got this very useful equation right here. And we've got this very useful equation. Okay, I'm not going to go through the whole derivation, but I want to point out that from these two equations, you can combine these two equations to derive other equations that are very, very useful. And I'm going to show you what those equations are. The first one, there's a way of combining these two that yields this, that v squared equals v naught, the initial velocity squared, plus 2 times a, the acceleration, times the delta x, x minus x naught. Okay, this is a very, very important equation that we're going to use a lot. Okay, we had this equation, those of you who took physics last year, we used this equation. I always call this the timeless equation. This is very handy because it allows you to calculate quantities when you don't have time. There's another equation, you can combine these in another way that will allow you to find the displacement x minus x naught. And it says x minus x naught is equal to 1/2 v plus v naught times t. Okay. So these are four very, very useful equations. Some people call these the big four. I referred to these last year sometimes as our kinematic equations. And these four equations are going to be used quite a lot. I want to point something out. That's that these three that I've starred are given equations on the AP exam. This one right here is not a given equation. So you don't need it. You can use these other three equations to solve problems. But if this is occasionally a handy equation, and so if you'd like to have it, you need to memorize that these other three are given on the test. We're going to spend a fair bit of time in coming chapters using these four equations to solve problems. These are going to be very important to us throughout the course of the year. So refamiliarize yourselves with these equations. Okay, that's all for now.